So this is the GCSE 9-1 physics. This is looking at the 2018 paper. This is P5 to 8 and P9 higher tier. This is paper 4. Now we're going to look at question 20. Question 20 is here. Okay, so a scientist uses different drivers to test the stopping distance of the same car. Look at the results. Okay, so the question is, most of the drivers tested the car on a dry day on a level road. Which driver tested the car on an icy road? Now, because it's icy, the brake will be slippery, so therefore the braking distance will be longer, and it looks like it is F because that's the longest distance. So F, if you look at the braking distance, that's 120. So driver F tested the car on an icy road. Which driver has the quickest reaction time? Calculate their reaction time. Okay, so you know that speed equals distance divided by time. You want to work out time, so time equals distance divided by speed. So you want this number divided by that number. 30 divided by 32, for example. So if you do 6 divided by 8, 13 divided by 16, 24 divided by 32, 12 divided by 16, 5 divided by 8, 30 divided by 32. And the one that has the quickest will be the one that has the smallest number. So it looks like it's E because 5 divided by 8 will be 0.625. So you would write 0.625 as the reaction time. Give two drivers that have the same reaction time. Drivers have the same reaction time. Explain your answer. All right, let's go back to the table. So here, if you look at A and C, that is 4 times bigger, and that is also 4 times bigger. So you can do 24 divided by 6 is 4, and 32 divided by 8 is 4. So it's the same ratio, same proportion. Let's have a look at part D. Show that the kinetic energy stored in the car at 32 meters per second is 614,000 joules. Okay, so you need to use half mv squared. So kinetic energy is half mv squared. So this is the equation. Kinetic energy is half mv squared, and you substitute m for 1,200, and the speed is 32 squared. So you just have to do this calculation on the calculator. 0.5 times 1,200 times 32 squared, and you get 614,400. I'm guessing that is to 3 significant figures. So 614,400 joules. So that is your answer. Describe what happens to the kinetic energy of the car as it brakes and stops. So as it brakes, the kinetic energy will decrease because it's stopping. Remember, kinetic energy is the energy of a moving object or moving thing. So if you're applying the brakes, the kinetic energy will go down. And also what happens to the kinetic energy? So you get transferred. So the tires, the kinetic energy will be transferred to the heat energy because there's friction. So the kinetic energy will be transferred from the motion of the car to the heat on the ground, the floor, the ground. So you might get some sound energy and you get heat energy. The braking distance of the car is 96 meters. Calculate the braking force. Right, so here you do force times distance equals energy. Force times distance equals energy. Work done. Force times distance is energy. Force times distance. So if you apply a force over a certain distance, that is work done. So you want to work at F. So D in this case is 96. You just worked out E, 614,400. However, the question says give your answer to 4 significant figures, and in the question it says 614,000. So if we were to use the exact answer, this will be the exact calculation, and if we divide that by 96, you would get 6400 newtons. I'm guessing we have to use their figure. So 614000. So here we have the exact answer was 6,400, but we're going to have to use their number. So if we do 614000 divided by 96, you get this number, 6396, to 4 significant figures. 6396, 6396, and that's in newtons. 6396 in newtons. That's in newtons, so the underlined part is in newtons. Alright, let's look at E. Driver B travels at 16 meters per second on the road. The thinking distance is 30 meters and the braking distance is 24 meters. Now it drives uphill at the same speed on the same road. How will driving the car uphill affect thinking, braking and stopping distance? The reaction time will stay the same. Okay, so the thinking distance is the reaction times the speed. Now, because we are given that the speed of the car is the same. Does it say that? Driver B, okay, so it does say that, yes, so look at the third sentence. Driver B now drives the car uphill at the same speed. So, assuming that the reaction time is the same, the speed uphill is the same, therefore the thinking distance. So the thinking distance will be the same. However, let me draw a diagram, force diagram. That's friction. It's going up. So here we've got a force diagram. So you've got the car, the mg is the weight of the car, r is the reaction of the car on the road, F is friction because it's going up. So because there is a component of the weight acting against the motion, the speed will slow down when he or she applies the brakes. So this one is the same. This one will decrease, and this one will decrease. All right, let's have a look at the mark scheme. 20. Okay, so it's F. So it's F on the icy road. E is the one that was 5 divided by 8. Because you do use speed equals distance over time, you want to work out time, the lowest time, smallest time, and time is distance divided by speed. It does say allow 6.25 there. Any two from A, C, or D? I think we picked A and C, didn't we? We picked A and C, yes, because that's 4 times bigger. Okay, let's go back. And yep, the kinetic energy is transferred to thermal energy. Good, so the kinetic energy is reduced, transferred. It gains thermal energy or heat. It does say allow surroundings gain thermal energy, dissipated to the surroundings. Yep, and then the thinking distance will stay the same, braking distance will decrease, and stopping distance will decrease.